Hello. Welcome to Physical Geography Virtual Lecture Extraordinaire. No, this is our lecture for Chapter 14. And hopefully this is not the worst virtual lecture I'll ever do. So let's just get right into it. So we're going to be talking about geohazards, earthquakes, and volcanoes. And so the first question is obviously, what is a geohazard? And that's simply any hazard posed to people by the physical earth. So we've talked about hurricanes and tornadoes, and now we're going to be talking about earthquakes, right? But it can be many other things. So landslides, rockfalls, floods, but also earthquakes, tsunamis, volcanoes, lots of different things. Okay, so let's start with talking about tsunamis. Now, oftentimes you might hear the term tidal wave, and that is because before we knew what caused them, one of the effects of a tsunami is before the big wave hits, the water from the shore pulls back, like a large wave does, and then comes crashing back. But tsunamis' waves are so large, it almost looks like the tide is leaving. So they were confused with tide. Tsunamis have nothing to do with the tide. In fact, they are primarily triggered by earthquakes. So hopefully this video loads. Okay, so I found this video online from Australia, so I'm going to kind of narrate it. But a tsunami is caused by earthquakes under the water. So here we have an example of what caused the earthquake that I'll talk about, or the tsunami in 2004 that I'll talk about in a little bit. You have two pieces of the crust like we talked about here in the bottom. Here's one, here's another. This one's subducting down under this, and that one's getting stuck. It's pushing, pushing, push. And then all of a sudden the pressure is too much and it breaks, an earthquake. And when it does, it basically causes these large ripples in the ocean. Very large, because these earthquakes move a lot of land. And like a ripple, it just travels across the top of the ocean. And you can see that in the middle of the ocean, if there's deep water, they can travel really fast. Fast as a jet plane. But they're only maybe 2-3 feet tall, which is a half a meter, so you wouldn't really notice it in the open ocean. They're not very high, they're just small ripples moving across very fast. But what happens is they move so fast, right, that as they get closer to shore and the bottom of the ocean gets shallower, they start to back up. You can see right here, they keep on coming in, but they start backing up and pushing and pushing and pushing, and these ripples just build. And what happens at the shore is you have a huge wall of water come ashore. So here, the ripples coming in, and the first wave comes in and crashes over the shoreline, and this is where they start to build. And before the water can really pull back, the second one starts coming back right away. So that's why many times when you see these videos, it looks like this big wall of water, not a huge wave cresting like a surfer. The water pulls back again, and then the second wave comes in. And usually, just like ripples on a pond, if you throw a stone in the middle of the lake, you get those ripples that kind of go back and forth for a long time. And these waves can be hugely damaging. So, all right, let's go back to close this. And let's go back to our lecture. And so this right here is an image of damage caused by a tsunami in 2004 called the Boxing Day or the Christmas Day tsunami. And this happened on December 26th, 2004, which is Boxing Day in some countries. And the earthquake's epicenter was right here off the coast of Sumatra. And you can see this represents the wave heights when they hit land. The darker the red. At the highest point, the waves were about 57 feet tall, right here in Indonesia, parts of the Andaman Islands, and in Thailand. All the way as far as Somalia, 3,000 miles away, the waves were still maybe 3 or 4 feet tall, but enough to cause damage. So this right here is an image of what the town of Banda Aceh looked like before the tsunami hit, and this is what was left after. And the big thing is not only does the wave come in ashore and then wash everything and break everything away, but as it washes back out to the ocean, it pulls a lot of stuff with it. So we can actually predict tsunamis quite well, mainly due to modern technology. We know that they're caused by earthquakes, and we can measure earthquakes, and we have satellite technology. And so they have these systems that we use throughout the world in different various areas that are prone to tsunamis. And so what happens, the way they work, is they have right here, anchored to the ocean floor, is called a tsunami meter. And right here, this right here is just a little sensor that has these floats attached to it. And when the tsunami comes through in the waves, it makes these bobble up and down, which triggers the tsunami meter. And it sends its data up here to a buoy, which then relays it to a satellite, which is then sent to a warning center on land. So what happens is when an earthquake hits near the ocean, these detect if a tsunami wave is formed in the middle of the ocean before it hits land. And so, for example, if there's an earthquake in Alaska, they can actually warn people in Hawaii and California and all on the west coast of South America of the possibility of tsunami. So the very first warning system was established in 1949 along the Pacific Ocean. There had been actually what I just talked about. There was an earthquake in Alaska that sent a tsunami across the ocean, and it killed a couple hundred people in Hawaii. So the U.S. government begins in 1949 with this. Eventually, it becomes the National Tsunami Warning Center. It covers all the Pacific Ocean. Okay. Now, the Indian Warning Tsunami System was established after the tsunami I just showed you in 2005. One of the issues, though, is a lot of the countries do not have the funding to operate it. So the Indonesian buoys had been established the year after that tsunami, but by 2012 they weren't working. And then, unfortunately, they weren't working very well. Another tsunami hit in 2018 and destroyed most of them. Okay. Now, tsunamis can happen in any ocean, like the Atlantic or the Mediterranean or the Pacific and the Indian. And so there's actually been several different efforts. They've tried to establish one in 2005 through the United Nations to monitor the Caribbean because there are earthquakes in Puerto Rico and Mexico and Honduras, all on the Caribbean. So they are at risk. Unfortunately, due to different countries having different funding, that's not always quite effective. Several countries besides the United States have their own independent systems. Japan has been struck by tsunamis repeatedly. You might remember a few years back, there was an earthquake that almost destroyed the Fukushima nuclear reactor, caused a huge tsunami to hit Japan. Japan has had this type of system in place for many, many years, and in fact has been credited with saving many lives just because they have so many tsunamis they practice for. Australia has one as well. All right. So this is one of the sections that a lot of students enjoy because everyone seems to be fascinated by volcanoes. Um, Many of you maybe made a volcano for a science fair project when you were younger, where you pour the baking soda in and the vinegar and it looks like foam and lava coming out. Okay. So volcanoes can be many things. There's three classifications. First one is active, and these are volcanoes that are erupting or have erupted in the last 10,000 years and could erupt again. If a volcano hasn't erupted in 9,000 years, that may seem like an eternity to humans. But in geologic time, remember the Earth is 4.5 billion years old. That's nothing. As long as that's considered fresh, if you will. Now, dormant volcanoes are those that have not erupted in 10,000 years, but still could. In other words, they still have a source or a supply of magma underneath and the ability to erupt. So these include volcanoes like Mount Rainier, which is right outside of Seattle. And then the last one are extinct volcanoes. And these are volcanoes that have not erupted for 10,000 years and have lost the ability. They've basically lost their source of magma. So we find these quite often as well. And then as for volcanoes that are erupting, three types. And we're going to go into these in details with their stratovolcanoes, which is probably what you picture in your mind when I say volcano, shield volcanoes, and cinder cones. So if you look at them in a cross section, you can see right here that a shield volcano is very low and broad, almost like a shield, whereas a stratovolcano Mount Fuji is the one that we think of, kind of that very tall, triangular peak. Interesting about Hawaii, one thing that, on a side note, that we think of Hawaii as an island in the middle of the Pacific Ocean, but really what it is the top of a volcano that is sticking above the ocean. The ocean floor right here is about 33,000 feet down. So what that means is, or I'm sorry, it's about 20,000 feet down. So the volcano that is Hawaii goes 20,000 feet from the bottom of the ocean, where it breaks the sea, and then it goes another almost 14,000 feet to the top. So altogether, from the top of Hawaii to the bottom of the ocean floor over here, it's about almost 34,000 feet, which is a mile taller than Mount Everest. Gives you an idea of how immense Hawaii really is. But we'll talk about stratovolcanoes, or often called composite volcanoes. And these are the most common ones. So this is Mount Fuji in Japan. It's got that kind of conical shape. So if you were a kid, you'd do a volcano like a big triangle. And it's called a composite volcano because it's actually made of layers. So if you were to strip it apart, you would see layers of different eruptions building up over time, right? And they are built up of layers of lava, which is rock that is molten on the surface that then hardens, and then pyroclasts, which are just basically volcanic materials. And we're going to go into those in a moment. But if you were to cut it in half, you would actually see these layers. And every time a volcano erupts, this magma and these pyroclasts come out of the crater, out of the vent, settle down the sides, and harden. And it just keeps on building and building and building, layer after layer after layer. Now, a shield volcano also erupts, but the difference here is the lava is much more fluid, more water-like. It runs faster, less gooey, if you will. And so the sides of the volcano are much more shallow, not as steep, much shallow, and much, much, much larger. So you can see again, they have the many, many layers, but they're just a much shallower angle. And they often have what are called flank eruptions because it's such a wide, broad volcano. The last one are cinder cones, and these aren't as common, and they're much smaller. And here, there's really an absence of liquid magma. There's very little liquid rock that erupts. It's mostly just chunks of rock and ash and dust. And so there's very little to hold these together. They're basically just cones made of cinders or dust particles. So if you ever have had a campfire and you put it out and what's left behind was kind of like pieces of charred wood and like ash and dust, that's pretty much what this is. So very, very short, very, very steep. So you can see there might be a little bit of lava, but it's mostly just ash and dust. So we've talked about what volcanoes give out. Most of us envision lava, so it erupts in hot liquid rock. Magma comes out, and like I said before, if rock is liquid below the surface, it's magma. Once it hits the atmosphere, it becomes lava, just a different name. So that's probably the most common, well-known product. But the other thing that comes out of volcanoes are gases. A lot of these rocks are composed of minerals like oxygen or sulfur or carbon. And so what happens is as this rock melts up through other rocks, it releases those elements into gas. So a lot of this gas comes out of here. Volcanoes are the largest supplier of carbon in our atmosphere. They give off more carbon every year than humans do, actually. And then pyroclasts in the middle, these are the things that are not gases and not lava, so chunks of rock and ash. So lavas. Now, we talked a little bit before. This was, I think, the last class before we went on this extended vacation, if you will. And lavas have three different types. So I talked a little bit, it has to do with silica, right? So we have mafic or felsic, and then in the middle, intermediate. Mafic lava has less silica, and felsic has lots of silica, more than 70%. What does that matter? Why does that matter? Well, one thing is this. Mafic lava melts at a higher temperature. So the temperature of mafic lava is much hotter, about 1,000 degrees, whereas felsic lava can be about 650. So a big difference in temperature. The felsic lava with more silica melts at a lower temperature. But the biggest difference is viscosity. So viscosity is how liquid is it? So again, I always use the caramel analogy, right? If you have hot caramel and you're putting it on something, if the caramel's really, really hot, right, it flows almost like water. It just flows like almost liquid water. But as it cools off, it starts to flow very thick, more plastic-like. And so mafic lavas are very, 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 they flow really easy. They have a very low viscosity. They're almost like water compared to felsic lava, which is more like just chunky, thick, almost like maybe brownie batter, if you will. And that is why shield volcanoes have mafic lava, have that very low silica. When the lava erupts, it just basically runs down the side like water coming off of a hill. It doesn't allow it to build those steep angles. Okay? Whereas a stratovolcano has that thicker lava. So it kind of just rolls down the side of the hill. And you can see the difference here. This lava is almost like chunky rock, and this is like liquid rock. And if it's really thick, really high amount of silica, sometimes it actually gets like toothpaste in a tube, and it plugs up the vent. And this is one of the dangers of volcanoes. If this happens, all that pressure behind it builds, and these are the kind of volcanoes that when they finally do explode, they just basically blow apart and explode like 1,000 bombs. Mafic lavas, the ones that flow easily, are the most common type, and they happen to be mostly under the ocean. So where the plates pull apart at the mid-ocean ridges, that's usually mafic lava. And it flows out right away and it hardens right away. The form is called pillow lava. This is the most common lava or magma on the surface. We don't see it because it's usually 2-3 miles down, so we don't think about it. But it's interesting that when they all the terms for lava and volcanoes, when they talk about volcanoes, all the technical terms are actually from the Hawaiian language. So this is called Paheohoi, Paheohoi, in the Hawaiian language, because that's where we studied volcanoes, was Hawaii, and so a lot of the terms were adapted. So smooth, billowy lava that flows out, they call it pillow lava, Paheohoi. I love saying those words. Whereas the lava that is kind of thick gets kind of blocky like that. In the rough, they call it ae, as in you step on it and you step on this with bare feet and you go ae. Now this is something that maybe looks only like a science fiction film. Sometimes in a volcano, in the crater, you actually have a lake of liquid rock. There's very few of these. In fact, there's only 5 known ones in the world. They do exist. If you want to see something kind of interesting, go onto YouTube and type in throwing garbage into a volcano. And scientists were throwing things into the volcano to see what the lava would do. Because that's for science. Right. Pyroclasts. So pyroclasts are things that are not liquid rock or gas. So a good example is ash. And ash is just all of the volcanic material like rocks that when the volcano explodes, it just pulverizes it to the point where it feels like flour. It's so fine, it's like dust. It's actually rocks that have been blown apart by the volcano. And when it gets up into the atmosphere, it eventually comes down. It looks like snow. This is actually ash from a volcanic eruption in the tropics. And it looks pretty, but sometimes these ash flows can be 3, 4, 5, 6 feet deep and bury towns. Another one right here is what they call lapui. And lapilli, these are basically tiny little like marble or pea-sized fragments of lava, tiny little rocks. And they're almost kind of like hailstones we talked about, that you can actually come inside and see the layers. So they were liquid lava, and as they cooled off, different layers formed. Many of you probably have used or have at home a pumice stone. And pumice actually naturally occurs. It's a volcanic rock that is so porous, it's almost basically like a big stone sponge. And this is part of a volcanic eruption. The magma erupts into the air, and it is almost frothy, and it cools off right away. So it has this very light feature. To be classified as pumice, it must be at least 50% air. And pumice is so light, it can actually float on the ocean. So a lot of times when a volcano that is under the surface erupts and gets closer and closer to the surface, the very first time it erupts, all that lava erupts right into the ocean. It cools immediately and forms these big, huge rafts of floating pumice that eventually settle down. And then, interesting one here are volcanic bombs. So this was actually a drop or a big, huge chunk of liquid rock that was exploded or thrown out of the volcano, flew through the air like a big raindrop of liquid rock, and actually cooled in that shape. So it's like a volcanic bomb. And then the last one right here is a volcanic block. And this is just nothing more than a big chunk of rock that was ejected from the volcano that wasn't pulverized or turned into dust. And if one of these was to fall on you, like it did here, and this is actually a real image, that would not be too fine. This actually here is near the volcano in Italy that is called Mount Vesuvius. Mount Vesuvius erupted many times, but this person died in the year 79 AD when obviously this big huge block fell out. All right, the last part we're talking about here is volcanic gases. So gas is not a pyroclastic material, but gas that is an eruption from a volcano, gas can actually cause the produce of pyroclasts. So a volcano can be plugged up, the pressure can go, and the gas and the liquid rock can behind that magma plug can actually basically, that's what causes explosions, which can make pyroclasts. But gas itself is not. Okay, it's kind of the fuel that does that. So volcanoes are usually pretty easy to spot on the surface of the earth. We can see them, they erupt, they leave very strong telltale signs. So some things that we often see are volcanic mountains, but also this process called columnar joining, and we'll talk about these igneous provinces and calderas, which is under my face there. So we kind of know what volcanoes look like, but columnar joining is interesting. This is when the magma erupts, the lava erupts. Sometimes it has this chemical property that when it actually cools, it hardens into these hexagon shapes, almost like a crystal pattern. And so when you look at it, it looks like someone pounded in all these stakes in the ground. It looks man-made. In fact, right here, this right here is in Scotland. Across the water in Ireland, there's another one of these. They call it the Giant's Causeway. Now, a large igneous province is just something that happens. It hasn't happened in recent modern human history, but there have been periods in the Earth's history where the Earth's surface just basically breaks apart and this large, huge, thin flood of basalt lava comes out and hardens. The movie that I had you watch, Making North America, talks about this. It hasn't happened for hundreds of thousands of years, but when it does happen, it can cover thousands of square miles. So these areas in red are all igneous provinces. So right here, for example, in northern Siberia, about roughly 250 million years ago, something happened to cause the Earth's crust to split open, almost like a dry scab, if you will. And thin, liquid basalt poured out and covered it in a big, thin sheet, roughly about maybe 10,000 feet thick, which is thin compared to the Earth. And you can see it right here, this layer. So there's some of them all over the Earth, and a lot of them under the ocean. The last form is a caldera. And a caldera is the remains of a volcano. I think of it like an acne scar. If you ever have a zit, right, and you know you're not supposed to, but you pop the zit in your face, and all the stuff leaves behind this little kind of empty place where the zit was, and that's what a caldera was. This is the part where there was magma. So here's what happens. You have a volcano right here, and then underneath is what's called the magma chamber, this big, huge, basically vat of liquid rock. But over time, the gas in the volcano begins to erupt, it expands, it swells. And if it doesn't release the pressure and erupt soon enough, it goes bigger and bigger until finally it blows apart the top, and what's left is this remain. Large, huge, almost like looks like a crater, but it's the remains of what was left here. Okay. Sometimes they're easy to spot. This is one in Hawaii, basically the caldera of an ancient volcano. Although sometimes they can be confused, this is actually a meteorite impact in Australia. But they can be quite large. The Yellowstone National Park here in the United States, this is actually bigger in area than the state of Connecticut. And this is a caldera, so this is a sunken depression right through here. And there is a lot of volcanic activity here. We don't see volcanoes in Yellowstone, but what we do see is liquid rock very close to the surface. So there's lots of hot rock under here, which causes lots of hot springs and geysers, which are basically water that gets boiled underground and erupts like a teapot. Now, that's not to say that Yellowstone has not erupted in the past. So this is where the Yellowstone caldera is. And there have been eruptions between 1 and 2 million years ago and about 600,000 years ago. And the eruption 600,000 years ago is so big that it covered this area that I'm outlining here in dark purple with up to, I think it was about a foot in ash. And over here, much more. If that erupted with the same force today, it would be more devastating probably than what we're going through now, being under lock and key. Here's another example. This is the remains of an island. This is called Thera. It's in the Aegean Sea near Greece. You can kind of see where it was. This part all blew away. One of the biggest eruptions in known history. Here's Greece, Turkey, Egypt right here. It was so large that the explosion was so large it created tsunamis that basically destroyed most of the cities around it. And many people think that might have been the original inspiration for the myth of Atlantis, because there was a city we find on the flanks of it that was buried under all this lava, and basically this island disappeared beneath the sea. So many people think that eruption might have been the basis for the myth of Atlantis. So what I'm going to do now, I'm going to pause the video here, and I'm going to stop it and start up on the next slide on part 2.